Now, before we do one single problem, just want to say that all the problems done in this video will be linked in the description. So there will be every single problem done will be completed in the description, and there will be a template of this whole worksheet. So what I recommend you do is before you watch the videos, you actually try to do all these problems by yourself. There will be a template of all these problems, and then I'll also include the solution. And if you don't have time, maybe you just click around on the solutions. I'll timestamp everything. This will be pretty user friendly. And this front page is actually really all the formulas we're going to need for everything. And yeah, let's just get into the first example. Okay, so we see that we have a fourth derivative minus 2 times the second derivative, and that is equal to 0. So this is a higher order homogeneous equation, and we're going to solve it using we're just going to solve it using a characteristic equation. So if we let m represent, let me say this better. We'll use m to describe the degree of this polynomial and relate it to the order of this differential equation. So m to the power 4 minus 2m squared. So what we've done is we're just kind of making a comparison here where we say, well, this is a differential equation and now we have a polynomial. And it's everyone can do polynomials, right? This is just algebra 2. So what we want to do is find the roots of this polynomial. So first I would start by factoring out a m squared, which we get m squared minus 2 in this. So you could already see that, well, two of the roots would just be m is equal to 0, and that has a multiplicity of 2. So that's pretty important, right? There's this m squared here, if you put 0 here, this whole thing will be 0, and yes, 0 is equal to 0. And if you do it again for another 0, that's also true. So I would write the multiplicity here and square it. And the multiplicity is important to remember that it is a multiplicity, because when you're writing your solution, you'll see that we need to factor in another x for a multiplicity. If that is unclear, you'll see what I mean when we actually write down our solution. Okay. Next we have m squared minus 2 is equal to 0. So if we get rid of this m squared and we just think about this part right here, just right here, what do we see? Well, this means that m is equal to plus or minus the square root of 2. Okay? So m is equal to precisely negative 2 and 2. Okay. So we have 4 values for m, 0, 0, negative 2, and 2, that would make this polynomial, if plugged into m, equal to 0. Okay, so if we have 4 values for m that are roots, then we must have 4 terms in our solution for the differential equation. Okay, so y is equal to c1. Now I'm going to write out this. Before I even do that, let me just write out the most general form, if you're unfamiliar. We usually write it as y is equal to c, some constant, e to the mx. Okay, and e to the mx, because everything is real roots here. Everything is real here. And totally made a mistake here, real quick. This is, my bad, square root negative 2 and square root 2. Okay, yeah, if you caught that, leave it in the comment. Okay, so if we apply this form to this, we'll have 4 things that look like this. Okay, so precisely, y will equal c1 e to the 0 plus x c2 e to the 0. And now that's what I meant by you have to factor in that x, because we had a multiplicity. So if we had a multiplicity of 3, if there's 3 m equals 0s, this would be x squared. Okay. Now the next one would be what? This, right? C3 e to the, why did I mess up drawing square root? Negative square root 2x plus C4 e square root x. Okay. So this is our actual solution right here, right? And this would build into this differential equation. Okay. Now for the rest of the video, I'm going to stop writing e to the zeros. We just have to recognize that's 1. But I did it for this first problem, just for your guys' viewer's sake. Let's just write this a little bit nicer. This is C1 plus C2 plus 230e to the negative root 2x plus C4e root 2x. Okay, now that is our answer for the first problem. Okay. Second problem, we have a second order differential equation, right? This is the second derivative. Okay, and we are given initial conditions here. So doing this problem will actually take a little bit longer because we do have these conditions that we have to solve for. Okay, let's write the characteristic equation, model this as a polynomial. Okay, now 20y. You should ask yourself, what order of derivative is this? And if you answer the question properly, it's 0. This is the 0th derivative. So then, what is the 0th polynomial? It's just 1. So this is 20 times 1. And we'll just write as 20. Okay. And this is just your algebra 2 right here. What I usually do when I answer these is I ask myself, is there a combination where something plus something is equal to this, and that something times something is the product of this. So if we think 2 times 10, well, 2 times 10 will not, however, if you put positives or negatives in 2 times 10 and write it as negative 2 plus 10 or whatever way you try to combine it will not equal this. If you 5 times 4, that will equal 20, but there's no way to make negative 5 minus 4 this or 5 plus 4 this. It just won't work. Okay, so it looks like we don't really have an easy factorable situation here. So what should we use? We should use the quadratic formula. So whereas m is equal to negative b plus or minus square root of b squared minus 4ac over 2a. Okay, and now we're just going to fill in what these variables are. So b is going to be negative 4. So negative 4 plus or minus, then b squared would be negative 4 squared, which is 16. Okay, and what's a? A is 1, c is 20. So that's ac, which is 1 times 20. Okay, and what's 2a? Well, that's just 2 times 1. Okay, well, let's simplify this a little bit more. Okay, 16 minus 80. I think it's 64. I think it's actually negative 64 in there. Okay. Let's think a little bit more here. Well, this would be 4 plus or minus. Now, if there's a negative 64 here, this is going to be an imaginary 8. So 8i. 2. I'm going to write this simplified once more again. It's 2 plus or minus 4i. Okay. So this is, this is what we would have that would make this polynomial true. This is the roots right here. So, but let's write this out. So if we take the positive route, if we take the negative route, I always write this as this. It would be 2 plus 4i, it would be 2 minus 4i. Now, that's not really that important of why I actually wrote that. I just wanted to do that for just later purposes, which you'll see. But this is in the form alpha plus or minus beta I. And that form is important because we have a formula for our solution where it is written like this. E to the alpha x, c1 cosine beta x. plus C2e to the alpha x sine beta x. Okay, and literally if we just fill this, fill this in with this of how it's supposed to correspond, that's our solution. It's as simple as that. So we see 1, okay, what's alpha? Alpha is 2, it'll be e to the 2x. And cosine beta would just be cosine 4x. Cosine 4x. And really it's just the same process again, just with a sine. Sine 4x. So this would be our general solution, but we can make this a little bit more specific because we're given initial conditions. Okay. So let's apply those initial conditions. So if y was pi over 2, if x was pi over 2, so if we put pi over 2 where all the x's are, it should equal to 0, right? So we would have c1 is equal to, why did I write that? It'd be c1 times e to the, we're going to literally put pi over 2 right in here, which would just be what? E to the pi. So this is like 2.7 times 3, which is roughly 3 times 3, 3 to the power 3, which is 27. Yeah, that was an engineering joke, right? You know, if you ever go on Instagram, you see those memes. This is cosine. Okay, what is cosine pi over 2? But we have a 4 here, so it'd be 4 times pi over 2, right? What is that? That's just cosine 2 pi. Okay. And again, the same process happens for the other term. C2 times e to the pi sine 2 pi. And yeah, this will literally just go to 0, which is really nice. So we're left with C1 is just C1 times e to the pi, because cosine 2 pi is just simply 1. So we have this is equal to this. What does that mean? Well, it means C1 is equal to 0, right? Because the only way to make this equal to this is if C1 is equal to 0, right? Because this is a constant. Okay, so C1 is equal to 0. That's an important piece of data. Okay, next thing we need to do, we need to take the derivative of our general solution, so then we can apply our initial condition. If we do that as, well, let's say y prime. Okay, so let's take this derivative here, and note that this would be there's going to be product rule in here, and there's going to be double product rule. So this will kind of expand a little big. 2c1 e to the 2x cosine 4x plus what? Well, now let's take this derivative again, but with respect to this part. So it would be c1 e to the 2x minus sine 4x. My bad, I forgot the minus 4. Minus 4, right? Because when you take this derivative, it's negative 4 sine 4x, which is I wrote over here. I just put the negative 4 in the front here just to make it look a little nicer. Okay, and the same process follows for this one. So it would be 2c2e to the 2x sine 4x plus 2, no, not 2, plus 4c2 e to the 2x cosine 4x. Okay, now if we apply our initial conditions, right, y prime of 0, no, it's y prime of pi over 2. So if we insert pi over 2 wherever we see x, it should apparently equal to 1. So let's see what happens. Okay. If we insert that into here, what do we get? It would be 2c1 e to the pi. If we insert it into there, right, it'd be cosine 2 pi. Okay, so if we insert it into this, It'll be 4c. Oh, right here, it's a sine, right? Sine, it becomes sine 2 pi. Okay, so we shouldn't even write this down. We should just write it as 0. So let's write minus 0. Oh, there's a sign again. Perfect. So plus 0. Okay, and then we have this one, which is not going to be 0. It'll be 4c2 e to the pi cosine 2 pi. And if we compute the value of this, right, the cosine 2 pi's are just 1. So this would be 2c1 e to the pi, 2c1 e to the pi, plus this, right? Because all of this is just equal to, this is equal to 1, so it's just 1 times this, plus 4c2 e to the pi. And of course all that is equal to 1. Now, we need to find what c2 is. But c1 is 0. So we could rewrite this as 4c2 to the pi. And if we just take these two facts and we solve for c2, all right, so it'd be 1 divided by 4, then it would also be times e to the negative pi. That is equal to c2. Okay, now since everything's getting stuffy, I'm going to make some space. Okay, so I made some space. So this is c2. This is our solution. And this is c1. So this will just be 0. Okay, now let's actually write all this. Let me write that now in on Jamboard. I was going to say in words, but it's numbers and variables. So we're going to plug this into the spot right here. 1/4 e to the negative pi times what? E to the 2x times sine 4x. So this is our final answer. This is our solution here. But we could make it look a little bit nicer. We could write it as sine 4x over 4 and write it as, so these are times to each other, right? They're times each other. If there's two powers times each other of the same base, right? You usually just add them. So if we just add these two together, it's going to be negative pi plus 2x. If you want to be fancy, write it as 2x minus pi. So this is your final answer right here. Well, actually, I mean, truthfully, this was 2, but this looks better. Okay, you're probably saying, oh, fuck. The algebra, right? That's what you're saying. At least that's what I would say, and that's what I would be thinking. But there is kind of a trick to these problems. The trick is knowing that it should work out nice. That's the only trick I could say. Because you know that like every single problem you ever do is from a textbook, so it's going to have to work out nice. And this is what you usually do right here at this part. So you write 3m3 plus 5m squared plus m minus 1 is equal to 0. Okay, well, let's rewrite this a little bit nicer. Let's rewrite this into something usable, because right now, like, that's still not really that usable. Now, what I'm going to do is split this 5 into a 3m squared plus a 2m squared. So 3m squared, 3m cubed plus 3m squared plus 2m squared plus m minus 1 is equal to 0. Okay, I'm going to stop saying equal to 0 because I actually will use the space. Okay, right here. What do these have in common? They both have a 3m squared in common. Let's capitalize on that fact. 3m squared becomes m plus 1. Okay, right here. Now I guarantee you, because this is from a textbook, like literally this is just how I do it. Like this is how I know, since this is from a textbook, that there's an m plus 1 inside of this right here. So if we just write m plus 1, and then we think about what else do we have to write right here to recreate this, that's how we can answer it. So if we just think real quick, okay, there's an m here. I mean, there's 2m squared here. So there's the next thing has to be a 2m squared. Okay, so 2m squared. Now we gotta think, okay, but there's an m here. It's just one m. So what does that mean? And there's negative 1 here. So somehow we have to create a negative 1. How can we create a negative 1? Just a plain simple negative 1. Well, we have a 1 here, so 1 times negative 1. There we go. And that's it. We just factored. This is like the hardest part of this whole problem right here. Okay. Well, let's rewrite this again, because rewriting everything is very important. So if we factor out m plus 1, because both, like these, this here and this here both have m plus 1 in common, so we can factor it out real quick. Now we get 3m squared plus 2m squared minus 1. Okay, damn it, my screen is not loaded. Okay. Now, so we write m plus 1, we factor it out, and we have a 3m squared plus a 2m squared minus 1. And my screen is still not loaded. Okay, now finally loaded. Okay. Well, this is all equal to 0. So if we just, like, since it's all equal to 0, we can just focus on this one for now. So m plus 1 is equal to 0. Well, then m is equal to negative 1. That's nice. Like, that's the fun part. M is equal to negative 1. You can just visualize that. Okay, now the next part. We could do, you know, by the way, what? Yeah. Here we go. Yeah, I see that. My bad. It's just 2m. And this will just be m. So I'm human, right? Okay, well, we could do some more algebra for this, but I'm going to be lazy, and I'm just going to use my high school quadratic formula. I'm just going to use my high school algebra 1 or 2, forgot which number it is, and use my quadratic formula here. Okay, unfortunately, I was talking for a bit, and my screen didn't update after I said algebra, I think. Well, good thing we didn't miss that much. So, again, apply a quadratic formula, fill it in as needed. Not as needed, fill in as oriented. Then we get this. So now we can start from here. Okay. So this is the same thing as negative 1/3 plus or minus 2/3. And if you don't remember, this was in the form alpha, not alpha. In fact, this is a real root, isn't it? It's not a complex root, so we're not going to do the alpha plus or minus beta I. It's not an imaginary root at all. This is completely real. It's just kind of ugly. But maybe it won't be so bad. Right? If we go like this, if we take the positive route, and we take the negative route, depending on the plus or minus, right? That's I'm saying the positive or the negative route. So if we think positively, what does this become? Well, it becomes 1/3. If we think negatively, it becomes negative 1. Okay, so this is a root, this is a root, this is a root. So we have a root of negative 1 and a root of negative 1 here. Okay. So our solution is going to be y is equal to c1 e to the negative x plus x c2 e to the negative x. Right, this is negative 1 and this is negative 1. Therefore, we have to account for that multiplicity. Okay. And then this will become c3 e to the 1/3 x. Okay. And if we apply conditions, right? If we apply conditions, this condition specifically, to this, what do we get? We'd say that y of 0. So we're going to put 0 into all of our x's, which is very nice here, which we get C1 plus, okay, look at that, that's times 0 here. So C2 doesn't even exist in this part, but we do get C3. And our initial condition says that that's all equal to 0. So, important piece of information, C1, C3 is equal to 0. Okay, now we need to take this derivative. Now, since I purely don't want these videos to get way too long, which they can, because I'm going to do like 20 problems, you're going to have to trust me on little things like this where I fast forward and just give you guys the derivative right here. Okay, so this is the derivative of this. Okay, now let's apply the initial conditions. I'm not going to skip parts where it's the essence of differential equations or things I think are important, but this should be your Calc 1, right? I can't go and make this whole video doing every little thing. Okay, if we apply initial conditions, so IO, initial conditions, what do they say? Well, they say y prime, and you plug that y prime, you put 0 in there, and you should equal 1. Okay, well, if we put 0 in here, put 0 in here, 0 in here, 0 in here. If we put 0 into this part, what do we get? We just get negative C1. We put 0 into here, we just get C2. And if we put 0 into here, we get 1 plus 1/3 C2. Not C2, C3. Okay, and that's all equal to 1. Okay, that's nice. So I'm going to underline this piece of information. I'm going to underline this one too. And we're going to take the next derivative and do the same thing. Okay, again, here we have the derivative, and now we're just going to apply initial conditions. So our initial conditions, I believe, let me move my face, it's this and this, right? So wherever you see x is now going to be wherever you see 0. So there'll be a 0 here, there'll be a 0 here. Well, the only thing that would be left is just C1. Okay, if we put a 0 in here, this is just going to become minus C2. And if we put a 0 in here, it's just going to be C3 over 9. Okay, so this is important. But what is this all equal to? This is all equal to negative 1. Okay, so now we have these three equations. They're all underlined. And we need to use these three equations to solve for our three constants. Okay, so I have this equation purely of just two variables, which makes it nice where I can use this to make a substitution to try to turn one of these equations just into an equation of two variables. Okay. C1 is equal to negative C3. Okay, and if we put this into, let's say this one, let's see what happens. It'd be 1 is equal to negative C1. So imagine there's a negative on this side, then this would be C3, right? So it'd be C3 plus C2 plus 1/3 C3. Okay, and then you could add these C3s together, which would get 4/3 C3 plus C2. Okay, well this is useful. What's next? Okay, let's maybe get rid of this C1 here for this one. So if we had C1 and we put a negative C3 in there, this would be negative C3 minus C2 plus C3 over 1 over 9, which is equal to negative 1. So now we have two equations purely just of two variables. Okay, let's simplify those two equations, make them into a lot neater of a form. 1/4 C3 plus C2, and this one is going to be, so this is negative 1, and this is 1/9, positive 1/9. We get negative 8 over 9 C3, which is equal to, not equal to, minus C2, which is equal to negative 1. Okay, let's apply this, right? If we maybe just make solve for C2 here, and oh, there's something better we can do here. So this is plus C2, this is minus C2 here. If we add these two equations together, we can get rid of C2. So if we add them together, this one's just going to be, and let me rewrite something here just for your guys' sake to make it look better. So if we add these two equations together, we get 0 is equal to 4/3 minus 8/9 C3. Okay. And what is this? This is the same thing as 12 minus 8/9, which is, okay. So as you guys can see, there's obviously a big conceptual moment where you should have saw that that was C3 is equal to 0. Okay, so let's erase all that. C3 is equal to 0. If you saw that before me, good on you. Okay, that's our important piece of information. Okay, if the C3 is equal to 0, then C1 is equal to 0 as well. Okay, now all we gotta do is find C2. So this is the equation that we can use to find C2. 1 is equal to, well, this is 0 plus C2. Okay, so again, just took the derivative, and this is it right here. Now, what you want to make sure when you're actually doing these problems is you want to go slow when you're taking these derivatives, because if you don't get these correct, I mean, actually, you need to get everything correct. What am I saying? You just get everything correct. That's the thing about differential equations. One little mistake leads to the next. And it's the equation. It's an equation of calculus, so mistakes multiply really quick. Okay, well, if we apply initial conditions, y double prime of 0, and that is equal to -1. So this would be, what would this be, right? Well, that would simply just be 1 times C1. The C2 would go away, because there's an x here, replacing all the x's with zeros. We get minus 2C2 plus 1/9 C3. Okay, so that's important. Okay, now I'm gonna make a little table real quick of all the important equations that we'll have that we need to solve in order to find our constants. And since this is the first example with a system of 3 equations, I will actually solve this, but for the next few examples, I will simply just display this equation and then show the values just to save time in the video, right? But remember, everything that I do will be on the slide, right? So you can always look at the slide for yourself. Okay, yep, I messed up solving it the first time. I gotta redo it now. Okay. So let's just focus on these 2 equations, and I want to get 2 equations, 2 unknowns, instead of having 3 equations, 3 unknowns, because that's a lot harder to solve. So if I look at these 2 equations, I just add them together, right? This goes away. So let's do that. What does that produce? Well, these go away. This is added, so it just turns into negative C2 plus C3 over 1/3. Not C3 over 1/3. C3 times 1/3 plus 1/9. And 1 plus -1 is 0. Okay, so this is really nice to have right here. So you could write C2 is equal to C3. Now this is 3/9 and this is 1/9, which is 4/9. Okay, so this is an important piece of information. Okay, so if I have this, what can I do? So this can help me turn an equation into purely an equation of 2 So let me just think. Doing these is always kind of tedious. I hate that word tedious. Don't use that. Doing these always takes a long time, and it's actually, I like to say these are mildly hard things always to do in math because it's you got to strategize to take the most efficient path, and sometimes you don't know what the most efficient path is. Okay, so let's just say I want to make an equation purely of C3. I'm going to pick this equation just because why not? But before I do that, I see that there's a C1 term in here. Let me change the C1 term. Use this equation to change the C1 term into a C3 term. So over here, we have C1 plus C3 is equal to 0. Well, then you could say that C1 is equal to negative C3. Okay, so now if you apply this fact and this fact into this equation and rewrite it all in terms of C3, let's see what we get. Well, we would get negative C1 would be positive C3 plus this plus C3 over 3. And this is all equal to 1, but before I do that, let me just add this stuff. This would be 2, 3, and if I divide everything by 9 as our common denominator, when I add these all, this would be 9 plus 4 plus 3. And this is C3, okay. 9 plus 3 is 12. 12 plus 4 is 16. This is 16 over 9. And this is equal to 1. As it says right here. Thus C3 is equal to 9 over 16th. Okay, now I'm going to put this in yellow because that's important. Okay. Now if we have this, and we have this, we could find C2 just with that. So C2 is equal to 9 over 16 times 4 over 9. 9's go away. This turns to 1/4. Oh, look at that. And if I have this and I have this, what does this mean? Well, this turns into negative 9 over 16. Okay, a lot. So now we can write our actual answer without having any of these unknown constants. Remember that this is our actual answer right up here. Okay, this is y is e to the negative x multiplied by what's in here. C1 is negative 9 over 16 plus C2. Okay, that's x over 4. And this is C3. C3 is plus 9 over 16. E to the x3. Okay, thank God. That's a lot of work for one problem. Fortunately, higher order differential equations, and this doesn't even have a right-hand side. These things take a very long time. Okay, now we're moving on to problems where it is a higher order differential equation, but we have a right-hand side, which is a function of x. Okay. Now, this would be a non-homogeneous higher order differential equation. And there's multiple ways to solve these types of equations, but the way we're going to do first is using the method of undetermined coefficients. And it's kind of like what we did earlier, this same process, finding the roots, right? And then creating a solution that way, except we do need to find a particular solution for this right-hand side. And then we got to add both of those solutions in the end. Okay, well, let's start off with what we know. Okay, well, we could write m squared plus m plus 1. And if we try to think about a factorable combination for this, maybe it is just m plus 1. So m plus 1, I know, well, m minus 1 would not be it. Yeah, so really, in this case, we should actually just jump to the quadratic formula. Right? Sometimes you have to ask those questions, can we find a nice factorable way? In this case, we can't. So m is equal to negative b plus or minus square root b squared minus 4ac all over 2a. And what would this be equal to? Well, this would be equal to, what is b in this case? B is just going to be 1, so negative 1 plus or minus 1 minus 4. What's a? A is 1, c is 1. Okay, and then 2a, that's just 2 times 1. Okay, well this is going to be negative 1 plus or minus, what is this? Well, this would be negative 3. Okay, so we can write this as 3 square root 3 I, right? Because if this is negative 3, then we have to show that it's negative 3 by writing this imaginary number in front. Okay. And yes, now that is, let's just write this a little bit nicer. This is negative 1/2 plus or minus 2 root 3 over 2 I. I'll put my face over here. So if we were to create a solution, what would that solution look like? First, let's call it yc for our complementary solution. Well, it'll look like, so look at that. There's an imaginary. Okay, so that means we're going to use our sine and cosine to help describe this. So it would be e to the alpha x cosine beta x plus e to the alpha x times sine beta x, where alpha is going to be this. Right, alpha will be this. Negative 1/2 x. I'm going to factor out that c1 cosine square root 3 over 2x plus c2 sine square root 3 over 2x. Okay, well, this is nice to know, right? But we do need to find what our right-hand side solution would be. So our right-hand side is x squared. Now we could describe x squared as a polynomial in its most general form of ax squared, ax squared plus bx plus c. And if we said that was equal to yp, so that's just like, what we do is we see our right-hand side and we try to describe it in its most general form, which would be like this. Yeah, what we're going to do now is we're going to try to find this stuff, find these constants, by recreating this differential equation right here using yp and yp's derivatives. Okay, so the derivative of yp is what? It would just be 2ax plus b. And then y double prime would be just 2a. So now if we recreate our dE, we'll write dE. So what's our dE going to be? It'd be this plus this plus this is equal to x squared. Right, and that's, we're going to recreate it using yp's here and its derivatives. So 2a plus what? 2ax plus b plus ax squared plus bx plus c is equal to x squared. Great, my screen's not updated. Okay, so my screen stopped updating for a second, but yeah, I just wrote out what I was talking about. Here it is. Right, this is what our differential equation is if we recreate it using yp and its derivatives, right, where this is yp. Recreate it. Okay. The reason why we recreate it is because we now need to find this. Now, what's important about these differential equations is that they're linear independence. And what that means is when we want to find these coefficients, we can just kind of drop things down. Okay, I'm about to freak out. My screen is not syncing with what you guys are watching, so I'm writing things and you guys aren't able to see it. Let's hope that's only the problem. Okay, so linear independence, right? I'm going to underline this term and this term. Why I'm doing that is because they both have x squared, right? So then if we just think about x squared here, a is equal to 1, right? Because this is ax squared and then this is x squared. So I literally just drop these down and then you can see that a is equal to 1. Okay, let's do that again for maybe, I'm going to use a different color. This one, this, yeah, okay, if we use that, those both have x's next to them. So it'd be like this, x to a plus b is equal to 0. Right, there's no plus x over here, so it's just equal to 0. And then we could just think about this as 2a plus b. And that's the same thing. Well, a is equal to 1, so let's just put that into here. So this is 2 plus b is equal to 0. Okay, well that means b has to be equal to -2. Okay, so this is important, and this is important. Okay, now let's just look at our constant terms, our left alone constant terms. We'll use a blue underline here. 2a plus b plus c. So if we were just to drop everything down, it'd be 2a plus b plus c is equal to 0. And the only thing we don't know is c. So if we just plug in these known values, it would be 2 minus 2 plus c is equal to 0. So c is equal to 0. Okay, there we go. And another way you could have thought about it is there is really, like, if you just look at it, right, c has to be equal to 0 because it's like you found what a and b is here, and c is just by itself. There's no other thing that really works with it, so it would just be 0. But you could show your work by doing this. Okay, so that's all important because now we could write our true yp. So I'm going to write our true yp right here. Not that this was not real, it's just there's unknown constants in here. And unknown constants, we could say it's undetermined. Undetermined coefficients. Method of undetermined coefficients, right? Yp is equal to, okay, what is a? A is equal to 1, so it's just x squared. What is b? B is equal to -2, so it would be minus 2x. And c is equal to 0. So this is, yeah, this is our particular solution right here. This is our complementary solution. And we're just going to add those together. So y is equal to yc plus yp, which is equal to e to the negative x over 2, parenthesis, c1 cosine square root 3 over 2x plus c2 sine square root 3 over 2x and plus x squared minus 2x. So that's our final answer. That is the solution to our differential equation. All of that right here. Great. Right there. Okay, for this next problem, again, it's like we're going to use undetermined coefficients, and we need to figure out a right-hand side solution for this. And this is Euler's formula, right? Well, first let's start with finding the roots, well, creating a polynomial that resembles this and then finding the roots of that polynomial. M squared plus 3m plus 2. We think about what can make this combination here. Well, if we write m plus 1 and times that by m plus 2, 1 times 2 is 2. M times 1, plus m times 2 is 3m, and m times m is m squared. Okay, so this is a good combination right here. This is our factorable pair. This is all equal to 0. So then we could see that yc is equal to e, one second, don't forget your constant, c1 e to the negative x plus c2 e to the negative 2x. Okay, there we go. We already found our particular, not our particular, we already found our complementary solution. Now we just need to find our particular solution. And we have Euler's formula. So right hand side is e to the ix. Okay, well this is a exponential. So how could we resemble a exponential? Maybe we resemble this as a plus bi e to the ix. equal to yp. That's maybe how we could resemble this. Now, this, right, this is the form that we can resemble it with. And I know this simply because, well, personally, I just have it, right? And if you go back, I actually forgot to write this in, and I looked at my private notes, and I should include this, I should give this to you guys. So these are our common forms that you'll see for your right-hand sides, and then you resemble it with this. Now, you may need to modify it a little bit more if you have a overlapping term of your YC solution and your YP solution. You may need to modify this by times it by X, and I'll show you an example of that. Probably the next problem we'll have will include something like that. But for this one, so far we don't have any overlappings, right? So this is what yp is equal to. Okay, so y prime p, right? What is that? Oh, well, that would be I a plus b I e to the ix. And remember that I stands for this, right? So if we rewrite this real quick and indicate that there's a bi squared here, well, that's kind of an important thing to do, because now we could see that if there's an I squared, right, if there's an I squared, it would just be -1. So this would be AI minus B e to the ix. Okay. So we need to take this derivative one more time. Y double prime P is going to be I minus B e I x, which would be, okay, so if there's an I here and I here, this would be -A, right? It's going to be -A. And so we'll write it as -A minus BI e to the ix. Okay, so now we can recreate this differential equation using this and this, actually. So our dE will be -I minus BI e to the ix plus 3 times AI minus B e to the ix plus 2 times A plus BI e to the ix. And I'm going to erase this now. Actually, I'm not going to erase it because maybe you want to keep that there for your sense. I'm just going to move it. Move it to over here. Okay, so this is the left-hand side of this differential equation recreated with yp and its derivatives, and we need to set equal to this. And as you can tell already, we can get rid of all these Eulers. I already called them Eulers. So this is also equal to -I minus BI plus 3AI minus 3B plus 2A plus 2BI and equal to 1. Okay. So now we can actually start finding what A and B is equal to. But maybe we should add things first, right? Okay, well, we have a -A here, a 2A here, A here. So let's just do regular A's first. We would have 1A. Okay, what's our regular? How many regular B's do we have? We have just 1 minus 3B. Okay, now let's think about our A's times I's. We have 3AI. Okay, we only have plus 3AI. Okay, what about our BI's here? We got -1 here, and we got 2 over here. So this would be plus BI. So this is now condensed into this, and is equal to 1. Okay, so let's just think about a minus, let's write a minus 3b is equal to 1. Okay, and then we got the same thing here. And if we factor out the I, 3a plus b is equal to 0. So notice that I picked like our coefficients that are not times I set them equal to 1. And then our coefficients that are times I set those equal to 0. Why I did that? Well, truthfully, I don't know why. I just follow the textbook. Right? Okay, well, let's go and solve. Okay. So this right here, I'm going to put it over here. So it would be A is equal to 3B plus 1. Right, I just rewrote this. Okay, now if I have this right here, now I can actually start using this information. So if I divide by I goes away. So now I'm just left with 3A plus B is equal to 0. Okay, that's nice. And then I could say that B is equal to negative 3A. Okay, so then now if I put this information into this, I could solve for A, and then I can solve for B later. So A is equal to, okay, let's put negative 3A right into here. It should be negative 9A plus 1, which is 10A is equal to 1. Thus A is equal to 1/10. Okay. And B, what was B? B is equal to negative 3A. So it'd be negative 3 over 10. Okay, that's A and B. Perfect. So we found A and B. Now we can rewrite YP. YP is going to be what? Where was YP originally? It's right here. So let's replace A and B with numbers. It'd be 1/10 plus, what's B? Minus 3/10 I, all times e to the ix. Okay, that's nice. Maybe we can write this a little bit nicer real quick before we should do anything with it. We could write it as negative 2I. Right? No, we cannot. We can write it as 1 minus 3I divided by 10 e to the ix. And remember, for our actual solution, it's yp plus yc. That's equal to our actual solution. So y is equal to this plus this. So c1 e to the negative x plus c2 e to the negative 2x. All of that plus 1 minus 3I over 10 e to the ix. And that's our final answer right there. Now let's just jump straight into it. Okay, m squared minus 2m minus 8. Okay, factorable pair, let's think about maybe it's m minus 2, m plus 4. Nope, it's the other way around. It's m plus 2, m minus 4. Right? 2 times negative 4 creates 8. 2m minus 4m is negative 2m, and m times m is m squared. So this is the correct factorable pair. And we can see that yc is going to equal to c1 e to the negative 2x plus c2 e to the 4x. Okay. Now let's think about our right-hand side. Okay, right-hand side, 9x e to the x, yeah, plus 10 e to the negative x. Okay. So polynomial of degree 1 times the exponential and exponential. Okay, so not equals. So yp would resemble this look. It would be something like ax plus b times e to the negative x plus e to the negative x. And it's not e to the negative x, it's positive x. Okay, there we go. And it's actually not just e to the negative x. We have to account for the fact that if we were to take this derivative, right, there would always be a number in front of here. So it'd be a e to the negative x. And let's not pick a, actually. Let's pick a different. Let's do c, this regular c. Okay, so this is how we could resemble the right-hand side using yp. Now, if we look at this, we have an e to the x and an e to the negative x, but we do not have an e to the x or an e to the negative x over here, so there is no overlapping terms from yc to yp, thus we do not need to multiply yp by any x or x squared or anything like that. So this is just, it's just that. Okay. Now let's take the derivative of yp. Okay, whew. This is just going to be e to the x, ax plus b, and plus e to the x times a. Move myself over here. And if we take this derivative right here, it's just going to be minus c e to the negative x. Okay. So that's y prime of p, y prime p, not y prime of p. Let's find y double prime, I believe. And we need to find y double prime because we need to recreate this differential equation. So y double prime is e to the x, ax plus b, plus e to the x a, plus e to the x a, minus turns into plus c e to the negative x. And let's rewrite y double prime p over here. This would be, okay, let's just factor out all the e to the x's. It'd be ax plus b plus 2a, and then plus c e to the negative x. Okay, so we have what we need to recreate this differential equation up here. Let's do that. Okay, well this would be, let's write dE. dE becomes what's right above it, ax plus b plus 2a plus c e to the negative x plus, not plus, minus 2 times this, all of this. So that's 2 times e to the x. Let me write this better. Use a bracket. Then now I'll use a parenthesis. Not use a parenthesis. ex, ax plus b plus a. So right there, I'm going to put this into here because they both share e to the x. And this is going to be minus c e to the negative x. Okay, now let's minus 8 of the regular yp, which is this, e to the x, ax plus b plus c e to the negative x. Okay, so this is our differential equation, and it is all equal to 9x e to the x plus 10 e to the negative x. Okay, now let's just, before we even try to find our coefficients, let's make this look a lot nicer. Okay, so I'm going to put all the e to the ex times x combinations right here. So x, e, x. It'll be a plus, not plus, it's going to be minus 2a. Okay. What's another one? Right here. It's going to be minus 8a. Okay. Well, that's nice. Now I'm going to just do all the regular e to the x terms. Okay. E to the x times b plus 2a. What's in here? It's going to be negative 2. B and a. So minus 2b minus 2a. What else? Negative 8 times this b, which is negative 8b. Maybe one more thing. Nope, that's it. Okay, now I'm just going to write all the e to the negative x terms. We have a c. What else do we have? We have a positive 2c. And we got a negative 8c. And again, all this is equal to 9x e to the x plus 10 e to the negative x. Okay, so this is a lot nicer. Now we can just kind of do our drop downs. Okay, so let's just focus on everything with x e to the x in front of it. And then what would that become? Well, if we focus on everything with the x e to the x in front of it, it's just going to be a. If we factor out that x e to the x in front of it, and we just think about what's in here and what's here and here, be a minus 2a minus 8a is equal to 9. Well, that's the same thing. What is this? This would be negative 10a plus a, which is negative 9a, is equal to 9. Thus a is equal to negative 1. Okay. Let's do the similar thing. So we got this group here, and oh, it's just that's just by itself, right? There's no non-x. It's not just e to the x. There's x times here, so this is all just by itself. So b plus 2a minus 2b minus 2a minus 8b. Why did I rewrite that? Let's just simplify it first. Okay, how many? Let's think about the a's. Okay, the a's go away. Oh, that's nice. Okay, so it's just b minus 2b, which is negative b minus 8b. That's negative 9b. And that's all equal to 0. Thus b is equal to 0. Okay. That's nice to know. Let's think about the next one. Let's do this in yellow. Okay, everything with e to the negative x. It's right here, and it's right here. So this would be c. This would be what? This would be 3c minus 8c, which is negative 5c. And that is equal to 10. Thus c is equal to negative 2. Okay. So now we can write our actual particular solution. Yp is equal to negative x. Okay, and b is equal to 0. And then what's c? C is equal to negative 2 minus 2 e to the negative x. Okay. This is nice. And this is also nice. Okay. Now we can just write our actual answer here. Oh, remember y is equal to yc plus yp, so we're going to add this and this together. c1 e to the negative 2x plus c2 e to the 4x plus, no, minus x e to the x minus 2 e to the negative x. Okay, there we go. All of that for all of this. There. Okay, I think this will be our last Yep, this will be our last method of undetermined coefficients example. And let's see what happens. All right. Auxiliary equation, let's not use that font. M squared plus M is equal to 0. Well, that's the same thing as saying M plus 1 is equal to 0. Thus, we see that M is equal to 0 and M is equal to negative 1. Okay, pretty fast. We already have our complementary solutions, which is C1. Let's just C1 plus C2 e to the negative x. Okay, let me move myself down here. Alright, so this is our complementary solution, and we got it pretty quick. Although, there's this differential equation, so something tells me that this problem is not just going to be as simple as just this. There's a little bit more we have to do, and we'll see what happens when we want to find the particular solution. So our right-hand side, that is x plus sine 2x. And yeah, this is a polynomial plus a trig function. So we could resemble it as ax plus b. And okay, now for constants, for coefficients, the next few things I'm gonna write, I'm gonna make them this cosine 2x and lambda sine 2x. The only reason why I picked these fancy coefficients is just because I don't want to get confused of writing c cosine 2x, right? Because c and cosine, I mean, that's like, I'll mess up later. So sometimes a trick is to pick coefficients that you'll definitely remember and not mix up. Okay. Now we're saying that this is equal to yp, right? Okay, but there's a problem, and I see it already. Okay, we have this right here, and we have this right here. So C1, imagine that there was a x to the power 0 next to it. So imagine there's x to the power 0 right next to it. It'd still be C1, right? Okay, so the point being is that sometimes you have to account for things like that. Or more easily, you can think of it as this, right? So there's a C1 here. There's just a standalone constant here. And there's a standalone constant here. So we definitely have some sort of overlap. And when you ever see overlap, it means that you have to times this part by x for its overlap. You keep this part the same because it's different and it's not overlapping with any of this stuff. But just this part does have some overlap. So yp is actually going to be equal to ax squared plus bx plus tritant cosine 2x plus lambda sine 2x. Okay, now I'm going to cross this out just so we don't look at it. Okay, so this is our actual, not actual, but this is our, yeah, it's our actual yp. We just need to find our coefficients, then we could create our actual yp. Okay, so let's find y prime of p. Okay, well that's going to be 2ax plus b, and that would be minus 2 tritant sine 2x plus 2 lambda cosine 2x, and then y double prime p. Well, that's just going to be 2a minus 4 tritant cosine 2x. And I know it's not actually a tritant. I know it's capital phi. I just like to call it tritant because it looks like a tritant. Right. Minus 4 lambda sine 2x. Now look at those lambdas, by the way. Come on. I mean, I think I got some of the best lambdas in the game. Yeah, nonetheless, let's keep going. Let's use these to recreate this right here. So our DE is what? 2a minus 4 tritant cosine 2x minus 4 lambda sine 2x plus this right here, which is plus 2ax plus b minus 2 tritant sine 2x plus 2 lambda cosine 2x, and that is all equal to x plus sine 2x. Okay, and then let's group our like terms, sir. So everything with just the x by itself, like this, I'm going to find. Underline in blue. Look at that, there's only one term. Very nice. So it's just 2a is equal to 1, right? Because there's a, like that. That's the way you can think about it. Okay, well this is really nice, because you can see that a is just equal to 1/2. Okay, now let's do another underline here. So let's think about all of our cosine terms. There's one here. Actually, do we need to think about our cosine terms? Let's think about our sine terms, because we have a sine term here. Sine, sine. We got two sine terms. And we would write it like this. Sine 2x is equal to negative 4 lambda minus 2 tritant, which is equal to 1, because there's only just a 1 on this side. Okay, and then if we ignore that sine 2x, we get to see that 4 lambda minus 2 tritant is equal to 1. Now we got to hold on to that piece of information and do a little bit more. So let's think about our cosine terms now. And I'm going to use a yellow cosine here. And cosine here. There's no cosine on the other side. So we have cosine 2x negative 4. It's not lambda. Negative 4 tritant plus 2 lambda. And that is equal to 0. Okay. So then we can already see that 2 lambda is equal to 4 tritant. Thus, lambda is equal to 2 tritant. Okay. Now let's put this information into this. Oh, by the way, notice that we have a b here. We still need to do that. My bad, I forgot about that little b. 2a and b. So it's just 2a plus b is equal to 0. b is equal to negative 2a, which is equal to, a is equal to 1/2. It's negative 2, 1/2. b is equal to negative 1. Okay. So, almost done. We just need to solve this array. Okay, what color I'm going to use? Black. I'm going to go back to black. So we get, let's plug this into lambda. Let's plug this into this lambda. That's what I meant. 4, 2 tritant minus 2 tritant is equal to 1. Okay, this is negative 8 minus 2. That's negative 10. Tritant is equal to 1. Thus tritant is equal to negative 1/10. And if tritant is equal to negative 1/10, then lambda is equal to negative 1/5. Okay. So all that is all nice. Now let's write what yp is actually running out of words to say besides actually. Let's just fill this in with what the variables are now. Be x squared over 2 plus, where's b? B is negative 1 to minus x, and plus minus 1/10 cosine 2x plus, what's lambda? It's minus 1/5 sine 2x. Okay, now we can add yp with yc and end it here. So that is c1 plus c2 e to the negative x plus x squared over 2 minus x minus cosine 2x over 10 minus sine 2x over 5. Okay, we get all of that at the end of it all. There we go. Okay, now we're going to have a situation where we can't use the method of undetermined coefficients because we have a secant, right? This is 1 over cosine cubed, so we can't use method of undetermined coefficients. So we need to use variation parameters. And before I even do that, I'm going to write out the steps to variation of parameters. So step 1 is find y1, y2, y prime 1, y prime 2. And this is like usual, right? Okay, what's step 2? Step 2, you're going to find the Wronskian, which is y1, y2, y prime 1, y prime 2. Okay. Then step 3. Okay, so let me write as step 3, 3a. u1 is equal to f times, nope, wrong way, y2 times f. Okay, now f stands for f of x. This would be f. And let's just say it was secant cubed divided by 3. It would be f divided by 3. Okay. So usually a is just 1, so you don't need to worry about it. But we may run into cases where it's not. And another way it may not be just 1. Let's just say it was x squared, y double prime. Then we need to divide y double prime by x squared. So we get rid of the x squared, and then it'll be x squared under here. So then a would be x squared. Now we're going to have a case like that later. But for this sake, this is your formula that we're going to use to find u1. And u2 is very similar. It is just kind of the opposite, where it's y1 f a w dx. Okay. Now 3b is where you do yp is equal to negative y1 u1 plus y2 u2. And then here's the final answer, is you just go yp plus yc is equal to y. And you're done. So that's the steps we're going to follow. Okay, now I'm going to move all of this to the right hand side. Okay, so we're going to start it off like usual. We do m squared plus m for this case. Not m, just plus 1. And you see that this is m is equal to plus or minus the square root of negative 1, which is 0 plus or minus I. Okay, so then you would see that yc, right, we usually write yc as what? Yc would be, it would just be c1 cosine x plus c2 sine x. There we go, that's all it is. just that. However, this is y1, and this is y2. Okay, so now let's compute y1 prime. Well, that is negative sine x. What's y prime 2? That is just cosine x. And let's just write down what f of x is equal to. Well, that is secant cubed. Okay. So now we can find our Wronskian. Okay, well, this would be, that'd just be cosine x here, and then sine x over here. And then it would be negative sine x, and this would be cosine x. Okay, and I could already see that this is going to equal to 1. I'll show you. So this is equal to cosine squared x minus sine squared x. So what you do is you multiply these two together, then you multiply these two together, and then you subtract them. And this is negative negative, so it's equal to 1, using your trig identity. That's very nice. This makes our life a lot easier. But it may not always be equal to 1. It could be equal to something terrible. But I can tell you, it's never going to equal 0, or else your equation is not linearly independent. And then you probably won't be doing this if it's not linear independent, because your teacher won't give you something like that unless they really want you to suffer and make you realize at the end of doing all this work. Okay, let's find U1. Okay, using this formula right here, y2 is sine x, and f of x is secant cubed x, and a is just 1 and w is just 1, so this is that. Okay, and I'm just going to write u2 over here. Oh, why am I? u2 is equal to, okay, it's the same w and say a, so it's just going to be over 1 right here. But what is y1? y1 is cosine, so it's going to be cosine x secant cubed x dx. Okay, these are the two integrals we need to do. Let's do the first one. So sine and secant, this is the same thing as saying sine x cubed x dx, which is the same thing as saying tangent x and secant squared x. Okay, so now this is where it gets interesting. We just have to do a substitution, although admittedly you could have done a substitution right here, which is what I did earlier, and I saw that it was just inefficient. So you should do your substitution over here. Okay, so if we think about substituting out tangent, we ask ourselves, what is the derivative of tangent? Well, it is secant squared. So okay, thank God, right? And I don't use the letters u here. I'll use anything but u. So I'll use mu. Okay. If mu is equal to tangent x, then d mu is equal to secant squared x dx. And we can use this information to write it as mu d mu, which is mu squared over 2. Then you can convert this now back to secant, back to tangent. So you get tangent squared x over 2. Okay, this is u1. Nice, nice, nice. Let me move this crap over here. Okay, let's find u2. It's going to be what? It's going to be cosine over here and cosine down here. which is secant squared x. Okay, so secant. Is there a identity we can use? Let's check the trick table. Oh, for some reason, let me move my. There you guys go. Okay, so we can use this one. We can write it as tangent squared theta plus 1. Okay, that works. Let's just think, maybe there's something better. Yeah, it looks like we're just going to write it like that. Hold up. Sorry. This is just tangent. Should have saw that. Right, I literally just said it right here. Like, oh my god. If you take this integral, you take this integral, then you get to tangent. Should have, I don't know. Sometimes you gotta realize that the textbook really doesn't want you to do a lot of work. They just want you to think a little bit. Should have saw that. Okay, this is tangent x. By the way, you can say, fuck off to your integration constants because they're just not important here in this case. Okay. Well, now we can see that yp is equal to negative y1, u1. Negative y1 is negative cosine x. u1 was tangent squared x over 2. And this is all being added to y2, which is sine x. And sine x is being times by u2, which is tangent x. Let's simplify this a bit. So this would be the same thing as saying a negative cosine x, sine squared x, cosine squared x. And let's not forget our 1/2. Plus a sine cubed x over a, that's wrong, sine squared x over a cosine x. Okay. Okay, look at that. So this is going to become negative sine squared x over cosine x times 1/2 plus sine squared x over cosine x. And these are the same thing, except one is negative 1/2 and one is a full. So it is just simply sine squared x over cosine x all times 1/2. And then we could rewrite this a little bit nicer. We can write this as tangent x. So we can write this as tangent x sine x over 2. This is what yp is equal to. Okay, now we can just add yc plus yp, and that is equal to y, which is what we actually want. Out of all this crap, we just want one variable, which is equal to one function. Just a lot of work for one thing. Where's yc? Yc is up here. Okay. c1 cosine x plus c2 sine x plus tangent x sine x over 2. Oh, stop. There we go. Ending right there. Now look at this differential equation. Ooh, that right-hand side. Let's see what happens. Okay, well, this part shouldn't be too bad. This part we like. Let's think about what this is. Well, this is this m plus 1 squared and is equal to 0. Thus, m is equal to negative 1. Multiplicity 2, right? And then we can see that yc is equal to C1. Let me write this better. Actually, no, I'll write it that way. E to the negative x and x C2 e to the negative x. Okay, so that's our complementary solution. This is y1, and this is y2. Okay. So if we take the derivative, well, let's just set up our round scheme first. So it goes y1 here, y2 here, and then the derivative of y1 and the derivative of y2 here. So the derivative of this is negative e to the negative x. The derivative of this, okay, now maybe I need to make my round scheme a little bit bigger. That's going to be negative e to the x plus e to the negative x. Don't forget your negative x right there. Okay. And I'm going to rewrite that. I know it does not look that nice. It's x minus 1. That's how we can rewrite it. Nope. It's called. It's 1 minus x. So that's this right here is the derivative of this. We just took out C2 because when we write y1, y2, we don't care about C1 and C2. Okay. Okay, real second. Let me just move this down. There we go. That's correct. Now y1. This is y1 right here. E to the negative x, and this is x e to the negative x. Okay. Everything is nice right here. This times this, it's going to be e to the negative 2x, 1 minus x, plus this, not plus, it's, by the way, it's, I skipped a step there, I don't want to skip steps with you guys right here. It's this multiplied with this, minus this, so that's why I wrote the plus. So it will be a plus in the end, but I'll just write a double negative. E to the negative 2x, x. Okay, and of course we're going to simplify this real quick. Let me just write it over here. W is equal to, I'm going to move myself over here now. W is equal to e to the negative 2x, and it's going to be 1 minus x plus x. This goes away, and it's just equal to e to the negative 2x. Okay, that's W. That's nice. Let's write another fact here. Well, f of x is, I'm going to move myself here. I should have just moved. F of x is this. So we get e to the negative x ln x. Okay, I don't know why I randomly put absolute value signs in there. I'm just so used to doing the integral where I always get the absolute. Just write ln x. Yes, and this is the same thing as this. Okay. So now let's just recall that yp is equal to negative y1 u1 plus y2 u2. Okay. And then what's the formula for u2? Well, u2 is the integral of y. And okay, let's start with y1 actually. I don't know why I went to y2. u1 is equal to y2 times f over w dx. And yes, there is a here, but the a is just equal to 1. So we don't really have to worry about it that much. Now, if we actually put values in this right here, what will we get? We'll have, where's y2? y2 is right here. Or you can just think of it right here. y2 is right here. X e to the negative x. What's f of x? It's right here. It's e to the negative x ln x. And w is e to the negative 2x dx. Okay. So as you can see, there's e to the negative x here times the e to the negative x. That's the exact same thing as this down here, and since they're the same thing, they will cancel. So we get really just x ln x dx. That is the integral we have to do. Okay, so let's do this integral. Okay, so I did this integral a different way than what I'm being suggested, and it just took a little bit longer. So I'm going to redo the back half of this, mainly because it's important to do the right integration technique instead of doing a one that takes longer, because we learned this to do good on a test, right? So we need to try to think about the fastest way we can do it. Okay, well, if we do integration by parts, but if we call u ln of x, earlier I called u x, which is usually nice because du just turns into dx and you get something really nice and simple, but this is a little bit more complicated. Du is 1 over x dx. Okay, and then if I call dv equal to ln x dx, not that, my bad, if I call dv x dx, then v is x squared over 2. And the formula goes uv minus integral v du. Okay, so now let me just insert everything as it is. So u times v, that is x squared over 2 ln x minus, and what is v? V is this. And what is du? Du is this. Okay, so I'm going to do all of this right over here. Again, remember that this is equal to u1. So we x squared over 2 ln x, that just stays. And this integrand, let's simplify it first. So it'll just be 1/2. Let me write it like this. Let me not do anything weird. Oh my god, I'm still doing something weird. X squared over 2. Why am I doing something weird? Yeah, just x over 2. Okay, just x over 2, right? X squared divided by x. There we go. Okay, now we can rewrite this as x squared ln x. And that is just x squared over 4. There we go. Okay, now this is nice. This is what we want. This is u1. But maybe we'll make it just a little bit prettier. Maybe we'll factor out the x squared over 2 and write this as ln x minus 1/2. And that just looks better. Okay, so we have u1. Let's find u2 now. u2 is equal to y1f over Wronskian dx. And what is y1? y1 is this. What is f? F is this. What is w? W is this. Okay, these go away. So the integral of just ln of x is x ln x minus x. Now, I do have this integral memorized, and if you don't believe me, I gotta adjust my screen. Here you go. That is just integration by parts. Okay, let's go back to this now. Okay, well, we just get x ln x, that's u2. Oh, very nice, very nice, okay. Now let's write out what yp is. It's negative y1, u1 plus y2, u2. Okay, negative y1 is negative this. Okay, and u1 is this. So let me make an edit. It'd be negative e to the negative x squared over 2 ln x minus 1/2. There we go. That's how you write it. and plus this times this, which would be x squared. Okay, now I'm just doing a little bit of factoring and math in my head right now, just so it looks nicer. X squared e to the negative x ln x minus 1. Okay, this is yp right here. Now we could rewrite it one more time. Should we? Why don't we? Okay, it's negative e to the negative x squared. I'll do 1/2 ln x minus 1/4 minus ln x minus 1. And that is equal to negative e to the negative x squared. Okay, 1/4 and negative 1. What happens? Oh, by the way, that should be a positive. This should be a positive 1 now, right? Positive 1. Okay, so now we're going to get 3/4 in here. So it'd be 1/2 ln x minus ln x plus 3/4. And we can actually even rewrite this once more. Again, you don't have to do this, but it just maybe this helps someone, learn a little bit of factoring and algebra and making something look nicer, right? You could write this as ln square root x over x plus 3/4. And we can even make this look like negative e to the negative x squared ln just 1 square root x. Okay, this is like the nicest it can look unless we want to start putting this stuff in here. So we're going to leave it like that now. So y is equal to yc plus yp. Yc is up here. Yp is over here. 1 e to the negative x plus xc2 e to the negative x minus, I'm going to write it x squared e to the negative x ln 1 root x plus 3 over 4. So this is our final answer. There we go. And by the way, if you look at the book solution for this, it's actually, I believe it's exactly the same thing. The only difference is that they factor their negative in here. So if you factor your negative in, this is negative ln x minus 3/4. And if you put a negative right here, then this gets flipped in here. And if it gets flipped in here, then it's, right, square root x over 1. And then you could factor out that 1/2 power out here, so then you get 1/2 ln x minus 3 over 4. And then, of course, this is a plus right here. So it's really just the same thing. They just even bothered to take more time to make this look even prettier. Maybe this is ugly in their opinion, but it's correct. Okay, this problem, it does give us this, right? I write in blue is what the book gives us. They give us this, so we don't need to worry too bad. Actually finding these would be pretty hard in my opinion, but they give us this, so we're going to use it. But we still need to figure out what f of x is. Okay, well, you can figure out what f of x is by usually looking at this, but is it just f of x? Or is it f of x divided by some a? It is this case. Remember I talked about this case? Well, here it is. F of x is just -1, x to the -1. And then a. A is this. A will always be whatever this is in front of the highest order derivative. So it's 2x squared. Now let's write this better, which is 1 over 2x cubed. Okay. That's good to know. Now we can compute our Wronskian. Okay, well, y1 square root x, y2 1 over x. Let's take the derivative of this, which would be 1/2 x to the negative 1/2. Okay, let's take the derivative of this, which is negative 1 over x squared. Okay. Times this thing by this thing, and this thing by this thing, and subtract them. And we'll see what happens. So this would be negative square root x over x squared. I'm going to not write this as square root x. I'm going to write it as x to the 1/2 over x squared. And it's going to be minus 1 over x times, what is this? This is 1 over 2 x to the 1/2. Okay, move myself down here. Let's compute this. It should be negative 1 over x to the 3/2. 1/2 minus 2 is 3/2. Minus 1 over 2 x to the 3/2. Okay, so these are both the same thing, except this one is 1/2 of it. So you could read it, if you don't believe me real quick, I'll just write it like this for you. Negative 1 minus 1/2. Should be plus now. Okay. Now you're going to notice I've just fast forwarded a second for us, right? And I wrote the value of the round skin right here. Now earlier, well, I edited it out, obviously. I said that we take the absolute value of this, which is not true. I searched it up online. So whoever I heard that from, sorry, but you're wrong, professor. Not our professor, but a different professor. So yes, oh damn it, did not want to do that. This is this, okay? This is a negative. Determinants can produce negatives and they can produce positives. In this case, it just happened to produce a positive, okay? But this determinant especially cannot produce a 0 because this is linearly independent. Okay, nonetheless, let's keep going forward. Okay, u1, oh, that's way too big, and that's messy. Okay, u1 is equal to the integral of y2 f times f, all divided by w and divided by a dx. Okay, what is y2? 1 second, let me expand this. There we go. What is y2? y2 is right here. So it'll just be 1 over x. Okay, and w is below, so then we have to flip this when we put it in. So it will be 2x 3/2 divided by negative 3. Okay, and f divided by a is exactly right here like this. 1 over 2x cubed dx. Okay, now let's make this a little bit cleaner. What do we got here? Well, this is a x 3/2, and down here would be a x to the 4. So let's write this as negative 1 over 3, x to the 3/2, x over 4, x to the power 4 dx. And by the way, the 2's can go away, as you see. And now we gotta ask the question, what's 3/2 minus 4? That's 3 minus 8 divided by 2. So it is equal to negative 1 over 3 integral x to the negative 5 over 2 dx. And now we can integrate negative 1/3, and we get x. So we add 1 to negative 5 over 2, which would be negative 5 plus 2 divided by 2, which would be negative 3 over 2 divided by negative 3 over 2. And we could write this as negative 1 over 3 times 2 over negative 3 times x to the negative 3/2 which, as you can see, is 2 over 9 x to the negative 3/2. There we go. Okay, so now we just got to do u2. u2 is equal to y1 over w times f divided by a dx. Let's insert our values. What is y1? y1 is right here. What is w? Well, again, we have to reciprocate this because it's in the denominator here. 2x 3/2 over negative 3. And this is f divided by a. Okay, let's simplify our integrand. Half power times a 3/2 power. We add the two powers. That is going to be, and by the way, the 2's can go away. We get x over 3 divided by negative 3x to the, by the way, this is not 3/2. Why do I keep writing as 3/2? It is 3. And yeah, this is not 3 either. This is 3. This is 1/2 plus 3/2, which is 4 over 2, which is 2. Now it's correct. Now we can integrate. This is negative 1/3 ln x. Okay, there we go. yp is equal to negative y1, u1 plus y2, u2. What is negative y1? It's this thing. I mean, what is this term? It's this term times negative this one. So I'll write it negative square root x, 2 over 9. Okay, now this is x to the negative 3/2, so I'm going to write it square root x times x. So these can go away. And this is plus, what's y2? y2 is this, that's 1 over x, and it's times this, negative 1 over 3 ln x. All of this is equal to negative 2 over 9x minus 1 over 3x ln x. And maybe we can factor out this, we can try to make this a little bit simpler. So we'll write it as negative 2. Wait, let's write it as, now, you know what, let's just keep it. Let's just keep it. Okay, yc, what is yc? They gave us y1 and they gave us y2, and this would be in the form c1, y1 plus c2, y2, which would just be c1 square root x plus c2, 1 over x. And this is yc, and then we add yc plus yp to equal to y. So let's do that now. Y is equal to c1 square root x plus c2 over x plus, no, it's not plus anymore, it's going to be minus, right, because there's a minus sign, just factor out the negative. 2 over 9x minus 1 over x ln x. Okay, now this is our answer. And yeah, there we go. Okay, so there's this equation right here, and we want to find yp using this stuff. Now, before I even do that, what I'm going to actually do is, I think it's important just to show you that you don't always need to use inverse operators, and you could actually use something maybe a little bit easier. And I consider this easier in my opinion, because I think the method of undetermined coefficients is easier than doing some of this weird inverse operator stuff. Okay, we'll just identify that this is P of D, and that this is Q of X. So if you recall, right, we usually have like this would be a differential equation if we go like this. Okay, and everyone agrees with that. So then if we just write it out a little bit nicer, is this way. And this is what we have now, right? And then if we just actually turn this into something that we would normally see, it's just y double prime minus y. Because d squared is not, this is not a polynomial, this means the derivative, the second derivative, this means second derivative right here. This means 0th derivative. So if you put y into here, it means y double prime. If you put y into this, it just means negative y, just like that. So right here is what you'd usually have, right? You'd usually have this, and you'd be asked to solve this. Now, what we're going to just do real quick is use method of undetermined coefficients, where you write this is, now we can represent this as a polynomial. And we could see that, well, m is equal to plus or minus 1. Thus, we could say that yc is equal to c1 e to the negative x, c2 e to the x. And this is, I mean, this is nice, right? This. And then we would see that the right-hand side, right, we always just say the right-hand side. We acknowledge it, we say it's 2x, and we say we could model yp as ax plus b. And then if we take y prime of p, y prime p, it's just a, and y double prime is 0. So, like I said, we're just doing method of undetermined coefficients real quick, just to show you that you don't always have to use this inverse operation, right? You could just try to reconvert this back into a differential equation, because a lot of times I just think this is easier, putting it back into a differential equation and recognizing it, and then using method of undetermined coefficients. Well, if we recreate the DE is simply 0 minus this, right? There we go. Ax minus b. And then look at this, you could already just read off that a is equal, well, negative a is equal to 2, thus a is equal to negative 2, and then b is equal to 0, thus yp is equal to negative 2x. So let's try to do this now using the method of, I mean, not using the method of undetermined coefficients. Let's try to use this using inverse operators. Okay, so I did it and I got the same answer, but I explained it terribly. So I'm going to do it again, try to make it a lot more friendly. Okay, so we already said that this is P of D and that this is Q of X. Now let's just note the form. Now this is from the textbook, that YP comes in this form, Q of X, P of D. Okay, and let's be even more precise with this, because what is this? This is 2x. So it's a constant coefficient times a polynomial. So we could write it as bxk. Okay, and p of d, yes, we'll just leave it as that for now. Okay, well, the formula for yp, it goes as following. Let's flip our page. Here we go. So this is what we had earlier, right? This is what we had earlier. It's right here. So we do have everything that we want. We have it just like this. Now we just need to, sorry, I keep switching. We just need to figure out how to use this to help us compute. Okay. So I'm just going to write 2x and then do d squared minus 1. Okay. Now we're going to pause for a second, and we're just going to do p inverse of d, and that is d squared minus 1. Okay. Now often we would call this AO. Okay. Now the reason why I'm mentioning all this is because there's the form, like YP, you could be a little bit even more specific with the way you call it. So I need to reference my notes real quick. You'd call it, you could do YP as this, B-A-O, and then I'm going to write series, dot, 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 right? Series, and just X. Okay. I will include this in the notes. No, I'm going to go back and add this in. Now, specifically this series, we got to pick the right one. So we need to pick one of these. Okay. So let's think about this. YP. Okay, so what's B? B is 2. What would AO be? AO would be -1. Okay, and then we don't know what to write yet. Okay. Now, let's go back to the series, right? I'm going to make an emphasis on this. It's 1. It's positive. It's always positive 1 in front here. And it's a plus or a minus Z. So we need to figure out what we want to call Z. Well, if this is AO, that means that AO was pulled out of this. So what I mean by that is we actually do know what this is. This would be 1. I'm going to make this in green to really emphasize this. 1 minus D squared. And here's this right here. Okay. That's important. Okay. And actually, I'm going to erase this little -1 over here because that's actually not completely true. If you write that there, that'd be a break of notation. So this 1 minus D squared, what does this look like? Well, it looks awfully like 1 minus, like this whole box right here, everything right here, this looks an awfully lot like this. And then we know what this is equal to this. This is 1 plus Z plus D squared plus C cubed dot dot dot. Goes on forever, right? So yes, what we're doing is we factored out AO. When I mean factored out, we just needed to turn this into a positive 1. So often what you do is you figure out what AO is, you write it here, and then you see what happens here. All right, so there's some algebra here in this part. Okay. And then right now what we're going to do is we're going to call D squared, just like this. Not negative D squared, just D squared equal to Z. Okay. So I'm going to write this in red. Okay. So let's start over here now. So YP is equal to -2. Okay. This is what this was, right? So I'm just going to write it using Z instead. 1 minus Z, -1, X. Okay. So far all I'm doing is just trying to assign different things, different names. Why we do that? Well, it's because math is complicated. That's why we do it. So here, yeah, all I did is just assigned everything a different name. Just tidied everything up here. So this maybe looks a little bit more nice and compact. Okay. Well, what can we replace this with? We can replace, so this and this is the same thing. And if this is the same thing as this, then we can replace this with this. So this is all going to become, I gotta stop saying that word, 1 plus Z plus C squared dot dot dot. Okay. So this -1, this power to the -1, right? This is the same thing right here, including the power to the -1 here, as the same thing as this. It's equal right here. Okay. So let's do a little bit more. So this is -2. No, did not mean for a bracket. Okay, now we should go back and we should swap out z. Okay, we should swap out z with what? Well, we should swap it out with d squared. This is 1 plus d squared plus d4, because z squared would be the square of this, which would be d4. Okay, now we can ask ourselves the question: how far should we keep going dot dot dot, right? How far should we keep expanding this? Well, this is why I did this first, right? Because we want to see what our actual equation looks like. Well, this is a second order differential equation. And it's second order because it goes to the second derivative. And this is the second derivative. This is the fourth derivative. So actually, there's nothing that's going to happen here because it would be equal to 0. So you can ignore everything past the highest order of the equation, okay? So now what we're going to do is we're going to apply, this is not saying this is x times -2. This is saying we have -2 times this operation. This is an operation that we're going to carry out, meaning this is not just like a multiplication operation. This is like really, I want to say it's an equation right here. This is a full-on equation right in here, or expression. Whatever. It's yeah, that'd be a better way. This is an expression we're going to carry out. Okay, and it's actually just a calculus 1 expression right here. It's an expression of calculus 1. So it's going to be 1, and we're going to apply 1 to x. And then we're going to apply d squared, which means it's not just d squared. This is not d times d. This is meaning the second derivative of x into x. Okay. So this is all like all we've done really so far, again, is just rewriting things, and now we're actually doing math. Like, we're truly doing math now. Okay, so this means 1. This is like, there's no derivative here. It's just 1, okay? So this is just going to become x. Okay, now this like right here, this is important to understand. This is asking us, what is the second derivative of this? Okay, and that's 0. So if we take its first, if this is just 1 right here instead of 2, it's just 1. This whole thing would just be 1, because it would just be saying the derivative of this. But this is asking specifically for the second derivative of this right here. So the second derivative of x is 0. Okay, now we get -2x. So that's a lot of work, in my opinion, for finding this right here, which I think we found this really fast. I think everyone was following along for this one right here. And here it's like, okay, there's kind of a lot of things going on, and in my opinion, this is going to be the hardest part of my test. Maybe if you're in my class, it'll be the hardest part of our test. And this was the simplest example, right here. Now, why bother to learn this, right? Well, we're going to learn this because method of undetermined coefficients can often arise a situation where you may not be able to find yp that easily. So you need to learn these inverse operations to find this. Okay, this next problem will be kind of similar, except we have a constant here, so let's see what happens. So let's write what p of d would be. Well, we can see that p of d would be d squared minus 1. Okay, so that's the same thing again, what we had before. And then we could see that p inverse d is going to be d squared minus 1, like this. And if we remember how we wrote that before, we wrote it as -1, 1 minus d squared inverse. Okay. And then how could we model this? Well, the series we used to model it was this one. That's the series you used to model this one. Okay, so, oh, do not want to do that. So I guess we could model this as negative 1, 1 plus z plus z squared, right? And I guess that would be the same thing as negative 1, comma. So let me just write this now in green. We're saying that z is d squared, just like we did last time. So this would be 1 minus, not 1 minus, 1 plus d squared plus dot dot dot. Okay. So this is all I did. I actually X'd out this term. That's why, or you could call I said that z squared dot 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 doesn't even exist in this point because it won't matter. So we got all those facts laid down. This is useful. Now it's really only useful if we know that yp is equal to p. Oh, my d's and p's are kind of looking like p inverse d applied to the right hand side, which is what we usually call q, right? Now in this case it's going to be this, which would be negative 1, 1 plus d squared. And all of this is going to be applied to 4. Okay. Well, what does that mean? Well, it means yp is equal to negative 1, where it's 1. So remember, there's no derivative here, so it's just going to be 4. And then now we're taking the second derivative of 4, which, as you know, would be 0. So this is just negative 1 times 4, which is negative 4, and that is what yp is. Okay, so yeah, so this answer is correct. I just did the wrong problem. I wanted to do a different problem, but yes, this is all correct. Everything I said was correct. It's just this problem might have been too easy. Okay, so let's do this other one, which will definitely be harder in my opinion because we're dealing with more orders here. Okay, so let's represent this again. This differential equation is a polynomial of derivatives. So p of d in this case would be d4 minus d cubed plus d squared. Okay. And yeah, that's all nice. Well, we want to make that p of d look something like this. So we got to figure out a way to do that. We could do that. We could do that by writing it like this, or it's the same thing as d squared on the outside. And what do we have? That would be d squared minus d plus 1. Okay. And then let's think about this. So d squared, and what can we can do this, we could write it like this, 1 plus d squared minus d. Yeah. Now the reason why I did all of that, again, is because we want this to look something like this, right? Now I'm going to write this something in blue. We want 1 minus, okay, I'm going to do both of these. I'm not going to write that one. 1 minus z to equal to 1 plus z plus z squared plus dot dot dot, or 1 plus z to negative 1 is equal to 1 minus z plus z squared minus z cubed dot dot dot. So right, like we want this p of d to look like this when we take its inverse. So we still haven't done its inverse yet, but it will. We're going to do that in a second. Okay. So let's recall that yp is what? It's equal to this thing. So we wrote that out earlier. So I'm going to write it as a fraction now. So what's Q? Q 6. 6 all under this. Okay. Now we're in useful territory. Okay. D squared minus D. Let's call it Z. Okay. Z is equal to D squared minus D. Okay. So then if we go like this, okay. So I'm gonna try not to make the mistake I did earlier. Well, this is gonna be 6 D squared, and right, since we made that substitution, and then we saw that this thing is the same thing as this thing, right? And we're making the substitution, so now we did this substitution purely just so we can get this now, right? So it's going to become 1 minus z plus z squared dot dot dot. Okay, there we go. So remember, like when you did the substitution, right? You wanted to find this thing, turn this thing into this form, and then turn it into this form, so you can get this up here now. Okay. And the reason why you can do that is because look, this is to the -1, and this is the expansion of it. Okay. So again, there's substitutions. These substitutions happen for a reason. Okay, so yp is equal to 6 d squared. Okay, now I'm going to replace all these z's back into d's. So it's going to be 1 minus d squared minus d plus d squared minus d squared. Okay, so note that I only went up to the fourth derivative, right? I only went up to the fourth derivative because we have a differential equation of fourth order. But, okay, so I could expand these out. I could expand these out 100%, and maybe I should, but the reason why I'm not going to is because you should look at this, right? Because what is YP? Like, what does YP mean again? It means we create this thing, and then we apply this Q. So if this was either a function, in this case it's just a constant. So we apply this Q into the D's. Okay, so we apply it into the D's. And if we take, so like, it means we take a derivative, right? So this would just, like the second, like the derivative of this would just be 0, okay? Right, this is 6 d squared. Okay. Now the reason why I didn't take the derivative down here and I just wrote it like this is because that's what I've been told. That's why. So now, okay, remember when I said, what type of notation do you use, right? Oh, this is the notation that we're going to use, and it's going to mean this. So, in other words, yp is equal to 6 integrated dx. So what does this become? It becomes yp is equal to 6 times the integral. So this little first one will just be x. And we do it again, then it becomes 6. Oh, let me erase that integral. 6x squared over 2, which is equal to 3x squared. There we go. So let's do another one where this is just a polynomial times a constant. So again, we write this as d. Oh, it's just going to be d minus 1. So I'm just writing this differential equation in operator form. Okay, and then we can see that this is going to be b, and that this is the degree. But I'm just going to call the whole thing q. So if I use my formula, or yp is equal to qp of d, but we should maybe be a little bit more specific because we have a 3 here, so we'll write it as b x k p of d. Okay, and then this turns into b over, so there's going to be, okay, so we're going to call it a. Now maybe I should go back. This is a. Okay. And it's going to be, remember, a series. Kind of like what we did for this one. Oops. Of course, times xk. So it's going to be pretty similar to the other problem that we did. Okay. So let's first find p inverse of d. Well, that would be d minus 1 inversed, which would be what? Okay, so it's not very useful yet, because why? We need this to be a positive 1, right? Like in both of these cases for the series, we have a positive 1 in the front. So factor out a negative 1 here, and write it as 1 minus d to negative 1. Okay. So as you can see, now we can start using this. So yp is equal to, look at that. What's b? B is 3. So it's 3 and negative 1 here. I know this looks ugly right now. 3 and it's 1 minus d. Okay. So if we use our series knowledge, we pick this one, write it as, what can we write it as? So we can write it as negative, damn it, negative 3. So 1 minus d, instead we're using our series knowledge, so this will become 1 plus d squared, and dot dot dot, and so on. Okay, so now we're actually at something that we can do, right? What does this mean? Okay, well, what this means is apply xk into d. So yp is going to equal to negative 3, and we're going to have 1 xk plus d xk dot 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 till, now I hopefully did not say this wrong the first time, but we're going to keep going, we're going to keep taking derivatives of xk till we get 0. Okay. So specifically in our case, this will be negative 3, and we're just not going to take the derivative, the first one, because it's just 1 here. So it's just going to be x. Now what's xk? Xk is x squared. X squared. And now we're going to take the derivative of x squared. Then we're going to do it again. So we'll call this d squared, x squared. And I'm just going to write d cubed squared. Now, obviously, this will not be a thing. So this will just, it will be a thing. It'll be a 0. So what do we get? We get negative 3 x squared, and we got to take this derivative once. It's 2x. Then we take this derivative 2 times. We take the derivative of this 2 times. So it's going to be 2x and then 2. And the reason why we don't take the derivative 3 times is because the derivative of 2 is 0. So it doesn't do us much good just to write 0. And this is what yp is. There we go. Okay, I really hate myself because I recorded this whole thing, these last two problems, and I deleted the recording because I thought I'm just going crazy. Okay, I'll go over it though. So this question wants us to find the equation of motion, amplitude, frequency, motion, phase angle, and the time of the particle when it crosses the equilibrium. So the key of this whole question is read this part right here. It says simple harmonic motion. And this is the equation for simple harmonic motion. And then you know that this is your well-known solution. Like these are just two well-known facts. The textbook will give you this solution because simple harmonic motion is just a very well-known thing. So you have this very well-known solution to this very well-known differential equation. Okay, and the fact that they give you that t is equal to 2 pi, well then you could see that if t is equal to 2 pi, and this is the equation for your period, which is 2 pi divided by omega, then omega has to equal to 1, right? Okay. And you can use this information, right, to find your frequency. So it's 1 divided by 2 pi. That's your frequency. You could simplify this if you wanted and get a decimal. I don't know why you'd want though. Or you could write it as 1 radian a second, right? Okay. Nonetheless, the next thing you want to do is you have your initial conditions that were given, which is 4 feet a second for your velocity and x equals -4 for your position. So that's right here. These are your initial conditions. And this is your x. So if you apply your initial conditions at t equals 0, you'd see that you could solve, well, you can't solve yet. Well, you'd see that this is where x is equal to 0. This is the equation that would correlate to x at 0, which is equal to -4. Then if you take this derivative, then you can use this initial condition. This is the derivative for x, which is the velocity. And then you could find that these two equations, you could make them both equal to +4. So have them equal to each other. And if they're equal to each other, then you can solve for your phase angle, right? Because there's a negative c on this side and there's a c on this side. So you could write just as -1 is equal to tangent phase angle. And then you could just read off from the unit circle that your phase angle is -π/4. Okay, so that's very useful. Nonetheless, you go back to this is not your true equation of motion yet, right? But this is your most general form for your equation of motion. So you look at your most general form for your equation of motion, and you say at t is equal to 0. Okay, well t equals 0 is just your phase angle in there, and that's equal to -4. Then you could solve for c, and this is the answer for c. And if you want to be really fancy, this is the nice looking answer for c. Okay, a little bit more. Okay, so you have your c, which is your amplitude, and you have your phase angle. So then you can write your equation of motion over here with all of its well-known qualities. And lastly, the question says, when is the time that the particle first crosses equilibrium position? So you set x equal to 0. So x is equal to 0 right here. And this is the equation of motion, which is equal to x. And then you could solve for t. And then you see that sine inverse of 0 is equal to t minus π/4. And then you could add the plus π/4 on the other side. And you can see that t is just equal to π/4 because sine inverse of 0 is 0. Okay, what's the next thing? This next question, I think in my opinion, is easier than the first one because it's asking for way less. So it gives you the amplitude, which is 10 feet, and it gives you the frequency, which is 2 CPS, and that's cycles per second. Okay, so this is your equation of motion. Although we didn't find it exactly this fast, we found the frequency, we used the frequency equation, and we found the period motion equation, and we set them, so we put this t, all of this stuff into here, which is this equation. And since this is equal to 2, then we get to see that omega has to equal to 4 pi for this to be true. So now you can put omega into here, which we did. However, we still don't have the phase angle. So we want the phase angle, but we can only find the phase angle by working on part B. So now everything from here on is part B. everything from here on, part B. So if we take the derivative of this equation, this is our result of that derivative. It's not very useful yet. What's more useful is using the position equation, which is right here, and setting it equal to 5, because it tells us to do that. If we do that, then this is equal to 1/2, because we divide by 10, and then we see that sine 4 pi t plus the phase angle is equal to 1/2. Okay. And if you take the sine inverse of 1/2 to just get this part by itself, well, sine inverse of 1/2 is equal to pi over 6, which is I wrote over here. Now sine inverse of 1/2 is also equal to this blue portion, which is 5 pi over 6. So this information right here is actually the most critical part to this problem, or part B, is because you don't have your phase angle. You actually will really never know what your phase angle is, and you don't know the time that it passes through this 5-foot mark either. So you have to substitute both of those unknowns for one known, which is pi over 6. Since this thing is common in this and this, then this pi over 6 can just go right in here and result for it. So x dot is equal to this and this. Because remember, you have this angle, which is 5 pi over 6, and pi over 6, and they both produce 1/2 if you take the sine of that angle. Both of these angles, they both produce 1/2. So x dot is equal to plus or minus 20 pi through root 3. Consider subscribing and liking if you found this video interesting or helpful. Leave a comment. Just leave any comment, just so I could, get this video pushed up the algorithm.